The learning objectives for this short presentation are to understand why and when we use the live load reduction and to think critically as to how various factors of safety are determined. At this point, we are all familiar with the equation for live load reduction and when to use it. But what does this actually mean? In understanding why, it will hopefully illuminate some details as to why we reduce live load for greater spans and are unable to use a reduced live load for small tributary areas. Live load reduction is a staple part of our pedestrian suspended footbridge design process. However, it must be noted that live load reductions are no longer up to United States codes. Like most aspects of code, live load reduction was first allowed because of probability. The chance of every meter along a 60-meter bridge is filled with people is very low. And the chance of a 100-meter bridge filled with people is even lower, which is why the reduction scales down with an increase of span. But for smaller areas, the likelihood of seeing a full load, such as on a suspender, is quite high. So we are not able to use a live load reduction. Overall, these assumptions still hold valid in the rural areas we serve, bringing us back to the point that EIA, along with many other experienced organizations such as B2P and Helvetas, continue to recognize live load reduction techniques in their pedestrian footbridges abroad. Next, we will discuss safety factor. The initial understanding for a safety factor is understandable. If you've ever been on a construction site, you may know that imperfections are inevitable. Factors of safety allow us to account for imperfections and represent the constant balance between extra safety and economy. However, what is more often overlooked is how factors of safety change. Why is it that we apply different factors of safety for cable analysis versus anchor sliding? Let's think about it. Imagine a cable snaps. Do the loads on other cables increase, decrease, or stay the same? Well, because no other factors in this equation are changing, they increase. And if one cable snaps, the chance of progressive failure or more cables snapping is high, making the resulting events catastrophic with a high chance of death or injury. Now imagine an abutment starts to slide. As this abutment slides, what happens to the forces? Sag decreases and horizontal tension decreases, so sliding forces also decrease. While this is by no means a preferable situation, is the sliding of an abutment likely to be as catastrophic as cable failure? Not likely. So to summarize, safety factors are ultimately often scaled by the risk of the failure for that specific design check. That is the end of our short presentation, in which you should now feel comfortable with live load reductions and safety factors. If you have any more questions or would like to hear more terms explained in depth like this, please reach out to the Bridge Program Coordinator or submit the feedback form at the end of every course.